Hello. In the previous video, I introduced linear transformations, and at the end of this video, I kind of give you an impression that I would use those transformations for some matrix operations. And now I will show you what I meant, because we are going to talk about matrix vector multiplication. And this will be a geometrical definition of this multiplication. Let's start. Matrix vector multiplication. And we start with linear transformations from R2 to R2. As I told you, they are entirely defined on the vectors of the unit vectors in the direction with the coordinate axis, so E1 and E2. If we have those two values of the transformation on these two vectors, then we can generate all the other values on all the other vectors. They will be simply linear combinations of the values on the unit vectors in the direction with the axis. And this is a consequence of this definition of linear transformation. Linear transformations preserve linear combinations. So if some vector was a linear combination of the unit vectors, which all vectors are, then its image is the same linear combination with the same coefficients of the values on these vectors. And now, if I put those two vectors, so the value of E1 and the value of E2, in a matrix, as they are, like column vector, this is the first column and this is the second column of the matrix, then I will define the product, the multiplication of this 2 by 2 matrix with a column vector in this way, that it is 2 times x plus 3 times y in the first row, and in the second 4 times x plus 1 times y. And it is exactly what we would get here if we perform this multiplication. 2 times x plus 3 times y on the upper row, and on the lower row 4 times x plus 1 times y. So this is how we define matrix vector multiplication for 2 by 2 matrices and column vectors with 2 rows. And if you remember dot product from school, then you see that we actually take dot product of row vector with the column vector in the first row, and the row vector, the second row vector with this column vector in the second place. And if we now take a general situation that our transformation is from Rn to Rm, we know then, exactly as in the previous case, that this transformation is determined by the values of the transformation on the unit vectors in the direction with the axis. And I wrote them as columns at once, because I told you that I'm kind of hinting for some matrix in the future, and the future is now, because we know that if we take any vector actually from Rn, then we will get the value of the transformation on this vector as this linear combination of the values on the unit vectors. And I will define the matrix vector multiplication in exactly this way. So you see that this matrix here is built of these columns, and if I multiply this matrix with a vector with n rows and just one column, then you see what I have done here. It's simply this kind of dot product of row times column here in the first row, in the second one the dot product of this one with this one, and so on and so on, and in the last one this dot product. And it is exactly the same result as we would get if we computed this linear combination. On the first place it would be x1 times a11 plus x2 times a12 plus, and so on and so on, xn times a1n. It's exactly this number. So we define matrix vector multiplication in this way. So let's have a look at this. If we now have any matrix, actually we don't have to think about this matrix as of linear transformation from Rn to Rm, but as we will see later in the course, each matrix is actually a linear transformation from Rn to Rm. Then we define the matrix vector product in this way, like dot products of the rows with this column vector in all the rows. But you understand by this definition of a matrix vector product that we have a natural restriction. In order to be able to compute this dot product of this vector with this vector, we need to have exactly many elements here in the row as here in this column, right? So the number of columns in the matrix must be the same as the number of the rows in this column vector here. So the matrix is m times n, and the vector must have n rows and just one column. Then if these two numbers are the same, so the number of columns here and the number of rows here, then we can perform this multiplication. The first one times the first one, plus the second one times the second one, and so on, plus the last one times the last one. It will give us the first element. And so on with the second element and the last one. So generally, matrix vector multiplication is the same as taking the image of the vector in the linear transformation defined by the matrix. So the columns of this matrix, here 1, 2, and the last one, the n1, are the images of the standard unit vectors in Rn. So now you know how to multiply a matrix with a vector, and we will use it for discussion of systems of linear equations, and later when we deal with matrices really in depth, then I will also show you how to multiply two matrices with each other. And well, it is for many reasons it's much easier to start with this geometrical definition, to think about matrices as of linear transformations, because then quite a lot of properties and rules for computations will just follow. You will see. Thank you for watching. Bye bye.